Hi, in this video, we want to take a look at determinants, and then we're going to look at orthonormal vectors. Okay, so for us, determinants really are just a mathematical object that we get that we use to get through our proofs so that we understand aspects of statistics. So really, determinants aren't really a big deal for us. We just want to understand them so that we can use them later on in other aspects, because ultimately we care about data analytics. That's what we truly want. That's what we truly are here for. All this math is great, it's important, but at the end of the day, I'm doing this just so that I can be a better data scientist, a better statistician, not for the sake of doing math. All right, now when it comes to the orthonormal vectors, that's different. All right, so when we talk about orthogonal vectors, we can think of if I have orthogonal data vectors, then I have actually really sweet data. If you take experimental design, you're going to study particular ways to come up with orthogonal data vectors. And how we interpret that is that we have like independence between our data vectors. And so in a way, we can look at it as a better way to measure what's going on. And this will enable us to measure or to get more information out of fewer observations of data, which is really good. A super important class is your design of experiments class. If you think about data analytics, the most important steps are the ones that are earliest, because if you make a mistake early on, that mistake or poor decision is going to propagate through your entire process. Experimental design happens before you even record the first observation. So that means it's super important. Now, another area that orthogonal vectors come up for us is when we do principal component analysis. In that situation, we take our predictor variables and we convert the predictor variables into a different coordinate system where all the coordinate axes are all perpendicular to each other, and that has some advantages to it, and we can get a lot of information out of those vectors. But for today, we're just interested in mathematics, really for the sake of mathematics. All right, so the determinants is a mapping from square matrices to the real numbers. So here, I'm going to say that A is a square n by n matrix, and the determinant of A, and so I'm going to put basically absolute value bars around A. It's not absolute value, but it looks the same. This is going to be a real number. Now, this number can be positive or it could be negative. It's just when you see the double bars, that is saying that it's a determinant of the matrix. Now, here, if you want to get into a more mathematical notation, it is a mapping. So the determinant maps the set of n by n square matrices to the real number line. And it can be anywhere along the real number line. It could be positive, negative, or 0. All right, in matrix algebra, we take the determinant, it's computed by computing all n factorial products of matrix entries. And we multiply half the products by a +1, half the products by a -1, and then we add up the products. Now, the positive or negative multiplication, the positive one, negative one multiplication corresponds to, is this an even permutation or an odd permutation in combinatorics? So let's talk about permutations. Okay, I'm going to start with a 2 by 2 case, then we're going to look at the 3 by 3 case, and we're just going to stop there because I just want to get for you guys to kind of see, where is this formula coming from? Why is it this way? Okay, so when I talk about two numbers, there are two possible permutations. 1 goes to 1, 2 goes to 2, the stationary permutation, or 1 goes to 2, 2 goes to 1. Okay, so in this situation, 1 goes to 1, and you see I have A11. 2 goes to 2, I have A22. 1 goes to 2, you see I have 1, 2. 2 goes to 1, I have 2, 1. Okay, so the determinant for a 2 by 2 matrix is going to involve this product and this product in it. A11, A22, A12, A21. Now, half of them are going to be positive, half of them are going to be negative. This one is going to be positive, and this one is negative. When I look at the formula over here, you notice that this is multiplied by a positive one, and this is multiplied by a negative one. Then I add them up. Okay. So let's move down to the 3 by 3 case. So here, I'm interested in the permutations on 3 entries. So the first permutation is 1 goes to 1, 2 goes to 2, 3 goes to 3. Now here, 1 goes to 1, 2 goes to 3, 3 goes to 2. Okay. So we can see that 2 and 3 are like switching with each other. Now 1 goes to 3, 2 is stationary, 3 goes to 1. So it's like 1 and 3 switch. 1 goes to 2, 2 goes to 1, 3 is stationary. So 1 and 2 switch. 1 goes to 2, 2 goes to 3, 3 goes to 1. All right, so here, all 3 points are involved in this permutation. So it's like 1 goes to 2, 2 goes to 3, 3 goes to 1. It's like a cycle. Now here is the same cycle, but in reverse, because here I've got 3 going to 2, 2 going to 1, and 1 going to 3. It's the same as this, but in reverse. All right, now, if I look through this, well, okay, so every permutation can be represented as a combination of 2 cycles. So here we have a 2 cycle. 2 goes to 3, 3 goes to 2. 1 goes to 3, 3 goes to 1. 1 goes to 2, 2 goes to 1. Here, this is a 3 cycle. This is a 3 cycle. All right, so I represent this with 0 2 cycles. I represent this with 1 2 cycle. Represent this with 1 2 cycle. 1 2 cycle. Now here, if you take a combinatorics class, this is 2. I represent this with 2 2 cycles. Don't worry about it if you don't understand this. Just nod your head at me. And here I can represent this with a combination of 2 2 cycles. All right, so 0, 2, and 2. Those are all even numbers. So these 3 products are going to get multiplied by a +1. Here, I have odd number of 2 cycles, 1, 1, and 1. These are all going to get multiplied by a -1. And so when I look at the actual formula, this is with a plus sign. This one is with a plus sign. This one is with a plus sign. This one has a negative sign. This one has a negative sign. And this one has a negative sign to it. And that's where our formula comes from. So you'll notice that this formula, it's long. It's one that, really we don't want to do by hand if we can avoid it. But if I go through, I can use the subscripts always correspond to a permutation on 3 different numbers. Now, if I want the formula for a determinant on 4 points, 5 points, 6, so on, I'll have to go through and figure out all of the possible n factorial permutations. And then if it's an even permutation, if it corresponds to an even permutation, I multiply by a +1. If it corresponds to an odd permutation, I multiply by a -1. And that's where this formula comes from. It works out that this has a ton of really cool, really exciting algebraic properties. Now, why does it work out that way? Take abstract algebra. You don't need to be a data scientist, but I really enjoyed this part when I was studying this in Gainesville. All right, so here's my 3 by 3 formula. And I can use that concept to get any determinant formula I want. But in general, what I want to do, I'm going to let the computer compute it for me if I need it in real life. I'm going to let R take care of it. It'll work it out. I don't need to worry about it. Okay, so here are some theorems, some special cases so that I don't have to suffer through this so much. If I have a diagonal matrix, then the determinant is the product of the diagonal, and that's it. So it's the product. And that corresponds to the stationary permutation. If A is triangular, so it's either upper triangle or lower triangle. So that means it's the diagonal, and the entries above are not 0. So upper triangular means that all entries below the diagonal are 0. Lower triangular means that all the entries above the diagonal are 0. In that case, we actually have the same formula as we do for the diagonals. And why is that? Because in the multiplication, those zeros come in and wipe out the other terms. And so if I have a triangular matrix, the determinant is the product of the diagonal. Now, if A is singular, then automatically, you don't need to compute it any further, you know that the determinant is equal to 0. Also, if the determinant is 0, then it's going to be singular every single time. Remember, singular means no inverse. Now, if it's non-singular, then the determinant does not equal 0. All right, what this does for us, if I see that a matrix has a non-zero determinant, I know it automatically has an inverse. Now, if A is positive definite, I know that the determinant is positive. Watch out on this proof though. Okay, if A is positive definite, then the determinant is positive, but it doesn't go the other way. Positive determinant does not tell me anything in regards to positive definite or not. No information. The determinant of the transpose is equal to the determinant of the regular matrix. And remember, we're only talking about square matrices. And if A is non-singular, means the determinant's not 0, then the determinant of the inverse is 1 over the determinant. That makes our life a lot easier when we need to work with these. All right, so now there's some special situations, special things to think about. All right, if I'm talking about a diagonal matrix and all the entries are the same, then it's just going to be the value on the diagonal to the power of n. And that follows straight from the formula we just looked at. Now, if I was to take that formula I showed you a moment ago for the 3×3 case, and I considered the situation where I multiply every single entry by a constant number, then I'm going to see that it's going to be c to the power of n times a. Boom. All right, so now let's think about the situation where I have block matrices. Okay, so I have a block matrix and it's in a 2×2 format. We're going to say that A11 and A22 are square, non-singular. Now, they don't have to be the same size. They could be the same size, maybe, maybe not. Then the determinant of A overall is going to be the determinant of the upper left-hand corner times the determinant that I get from doing this multiplication and subtracting it off from A22. Now, I can switch this up. If I like anchor on A22, then A22 determinant multiplied by this weird mathematical operation, it will also give me the same value. All right, so now, corollary. So remember, a corollary is something that I get for free from a proof without having to do any additional work. If I have a block matrix and I have a 0 block off the diagonal, then the determinant is equal to the determinant of the diagonal blocks. Makes life a little bit easier. Another corollary is if I'm in the situation where the block in the lower right-hand corner is a scalar, so it's a 1×1 matrix, that means that here, these two are, I have vectors, and it's going to be the same vector. Then what's going to end up happening is we're going to take this particular scalar value is going to be multiplied by the determinant of the upper left-hand block matrix determinant, and that gives me the determinant of A. So in this situation, we need to make sure that A11 is non-singular, and these two, A12 is a vector, and A22 is a scalar. Another corollary. So in this special situation, I've got a matrix in the upper left-hand corner. I've got 1 as my lower right-hand corner block matrix, and then I have C negative C transpose off the diagonal for my block matrices. Then I get a special formula that the determinant of B plus C times C transpose. So this will be an n by n matrix. N minus 1 by n minus 1 matrix added to B. The determinant is this particular formula. And we derive that just by crunching it out. All right, now, if A and B are the same size, square matrices, so the reason why I have this hypothesis in here is that for multiplication to be defined, then the determinant of A times B is equal to the determinant of A times the determinant of B. This, in abstract algebra, is kind of a big deal. This is one of the important proofs that you will have to suffer through if you become a math major. All right, the corollary of this is that the determinant of AB is equal to the determinant of BA. Why is that? Well, because this determinant and that determinant are scalar values. So this is regular old elementary school multiplication. Elementary school multiplication is commutative. I can switch the order and I can change it into the determinant of B times A. Another corollary we get, see, we're getting lots of corollaries off of this proof. The determinant of A times B, the corollary, let me back up. The determinant of A squared is equal to the determinant of A squared. All right, so these are the big theorems that the most important one to know for us is going to be the determinant of A times B is equal to the determinant of A times the determinant of B. That is going to be the most important one. The other thing that you absolutely must keep in your head for the rest of your life when you deal with mathematics is that the determinant, if it's equal to 0, it's a singular matrix, no inverse. If it's not equal to 0, it's non-singular, the matrix has an inverse. That is going to be critical wherever you go in mathematics. And then if A is non-singular, then the determinant of the inverse is 1 over the determinant of A. This list is an important list to know off the top of your head. Like these, you need to be boom, 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 boom. Those of you who are math majors or took a serious matrix algebra course, you already know it. All right, so now let's talk about orthogonal vectors and matrices. Okay, so two vectors are orthogonal if and only if the dot product between them equals 0. Okay, so the dot product is where I take entry-wise and by position. I go through and I multiply first position together, second position together, third position together, all the way down to the nth position. Then I add it all up. That is my dot product. All right, so I can just see that it's this formula. And two vectors are orthogonal if and only if this sum equals 0. And so this is the same as A transpose times B or B transpose times A equal to 0. Okay, so something that is going to be very important in a lot of situations is understanding the angle between two vectors. Okay, so if I have two highly correlated, but not perfect correlation, but nearly perfect correlation between two vectors, then you can think of it geometrically as the angle between them is super tiny, like they are like really close. They're not parallel to each other. There is a tiny angle between them. All right, in terms of statistics, if they're close to being parallel to each other, two data vectors, then I can overfit. If I have both of them going on in a linear model, I can overfit off of those. What I prefer to see, I like to see data vectors that have an angle like this, 90 degrees. Ideally, we will have 90 degrees between all of our data vectors. What we don't want to have is a bunch of vectors where the angle is very, very shallow. It's a very small angle. In that situation, they're nearly parallel to each other. They have high correlation, and that means that including multiples of these multiple vectors in our linear model means that we are prone to overfitting. So this cosine business gives us a way to measure this. And if you took stat theory, I'm sure you know the connection in the Casella book between the between correlation and the cosine. All right, so yeah, usually when we're dealing with this stuff in data, we're taking like x minus x bar, y minus y bar, stuff like that. Okay, so the dot product between two vectors is equal to the length of each vector times the angle between them. So if you took calculus, you know this pretty well. And this angle, I'm interpreting this in higher dimensional space. So if I have 1,000,000 observations, then I'm dealing with vectors of length 1,000,000. And so 1,000,000th dimension space is a higher dimension. So we have to kind of accept the idea of angles in higher dimension space for this to be conceptually coherent. All right, so how do I prove this? Well, we just do a little bit of trigonometry. Easy peasy lemon squeezy. What I'm going to do, I'm going to take law of cosines from back in high school. I'm going to take this triangle. So I've got vector A, I've got vector B. And these two vectors are hanging out in higher dimensional space. This is the origin of my coordinate system. All right, well, if I think about it, this vector is parallel to the vector B minus A. So it's not technically, if this was truly correct, this angle would be coming off of the origin, but it's easier to explain this way. So the length here is the same as the length of B minus A. Okay, so if I look at this, that's a triangle. And I see angle, opposite side, adjacent side, adjacent side. Okay, so I know all sides, I know one angle. Well, I can use the law of cosines. If I think about the law of cosines, the length of this part squared is equal to the length of this squared, length of this squared, minus 2 times length cosine of that angle. That's just the law of cosines. Okay, so then what I do, basically I just plug and chug. I just work it out. It works out beautifully. And I didn't do this as directly as I could have. I was just writing it out, but it works out all the same. So I just go through and work it out. Remember that when we talk about the norm squared, that is the transpose times itself, its own transpose times its own vector. And so I just work it out. It's beautiful. It's wonderful. And this has a direct connection to correlation, where I'm dealing with a data vector minus its sample average. All right, so when the angle is 90 degrees, then the dot product will be equal to 0, since cosine of 90 degrees is equal to 0. Okay, so that's the idea of perpendicular vectors, orthogonal vectors. So let's talk about normal vectors. Okay, in mathematics, what we do, we reuse terms. If you go into education, what the people do, they change one little thing and they come up with a whole new terminology, whole new dictionary of terms for something. In mathematics, what we do, we reuse words instead. So when you see the word normal in mathematics, it can mean a whole bunch of different things. Normal is used in here, it's in matrix algebra. It's used in physics for the normal direction. That's what you feel when you're doing a sharp turn in your car. You've got normal topology. You've got a normal subset in abstract algebra. Every field uses the word normal. When we're talking about mathematics, if you see the word normal, you need to go, hey, what type of normal are we talking about? For us, a normal vector is a vector of length 1. Okay, so why do we like normal vectors? Well, it standardizes what we're working with. And so it makes it easier to interpret what's going on. So a vector of length 1 is called normal. Okay, so if I take the length of the vector, the 2 norm, which is equal to the vector transpose times the vector square root, that has to be equal to 1. Now, any non-zero vector can be normalized. So remember, remember how you like normalize stuff? You do your z-scores, you subtract sample average divided by standard deviation. This is like very, very similar. All right, if I take a vector and I divide by its length, then the new vector is going to be of length 1 every single time. Okay, so when I want to standardize my vector length, then I go ahead and do this. By the way, this is something I do on my data is I always divide by the sample standard deviation when I'm doing variable screening. Why do I do this? I do this so that when I look at, let's say like I look at the standard error when I'm looking at the coefficients values, that you'll notice that if you go through and you standardize all your vectors and then you start doing your linear models, your standard error of the vectors will be more similar to each other as long as you don't have a bad collinearity going on. And so that helps me screen for what's going on for when I start doing my machine learning and start doing my random forest and start doing my data prep. So this divide by the length is a very powerful idea for us. Now, orthonormal vectors. All right, these are the vectors we want. These are like the holy grail of data. If you take design of experiments, you will spend a lot of time looking at ways to basically get vectors that correspond to orthonormal vectors. So this is where all the vectors are perpendicular to each other. So now, the properties that I like to have, if I can get them, data comes as data comes, but if I have the opportunity to work with it, I want them to be orthogonal. I want them to all be perpendicular to each other, and I want them to be of length 1. That way it standardizes things as I do my variable screening. Okay, so an orthonormal vector set is where I have a bunch of vectors, and when I take the dot product, either I get 0 or I get 1. So I get 0 if they're not the same, and I get 1 if they are the same, because then that is the norm squared. All right, so if I'm in the situation where somebody hands me a bunch of vectors, and those vectors have this property where I get 0 or 1 from the dot product off of the i's and j's, then that set of vectors is called an orthonormal set of vectors. So ortho means that they're perpendicular to each other. Any two I grab are going to be perpendicular as long as they're not the same, and the length of each one is 1. Now, if I take a bunch of orthonormal vectors and I slap them together into a matrix, then that's called an orthonormal matrix. All right, so a proposition. If C is an orthonormal matrix and square, then C transpose C is the identity matrix, and C times C transpose is also the identity matrix. So it works out that if C is orthonormal, then C transpose is also orthonormal. The best example of these are the permutation matrices. All right, so now let's talk about rotating axes. If I have a vector and I multiply by an orthonormal matrix, this is equivalent to rotating and reflecting the vectors about the axes. So I can think of it as I have a different coordinate system potentially. Multiplying a vector by an orthonormal matrix does not change the length of the vector. This is important. It doesn't change the length of it. So if I need to do a series of transformations, I want to preserve lengths, I can use orthonormal matrices to achieve this goal. And the last part I got for you is if A is a P by P matrix, C is a P by P orthonormal matrix, then the determinant of the orthonormal matrix is plus or minus 1. C transpose A, C determinant is equal to A. Well, that comes from this part aspect and the multiplication property for determinants. And furthermore, if anytime I'm dealing with an orthonormal matrix, all of the entries of that matrix are going to be between -1 and 1, assuming it's a real matrix. If you have complex numbers, we have corresponding results that deal with the magnitude, but we'll leave that for somebody else to deal with because we're keeping it real, yo. All right. That's all I've got for you. I hope you're doing well. Take care and goodbye.